Our first example of simulation is a simulation of a queuing system. In this example, we have one nurse and one doctor in a small office. Patients arrive randomly. Each patient goes to for a checkup with the nurse and then for a checkup with the doctor. They may have to wait before being served by the nurse and then before being served by the doctor. Service priority is first in, first out. Service time of the nurse is always 7 minutes, but service time of the doctor is random, and also, of course, arrival of patients is random. So we have here a distribution of time between arrivals of patients provided in this table, and service of the doctor. The time of the service of the doctor is random also, and the distribution is provided in this table, right? And these distributions are discrete, but that's just for simplicity so that we can simulate it easily by hand. But if you simulate it using computers, you could use a more realistic continuous distributions. Now, we are interested in this simulation in the average time a patient spends in the doctor's office from the moment they arrive till they leave, right? So first thing to realize is what is the system, what does the system look like? So the system, right, when patients arrive, they start at the nurse, but before they get to the nurse, they actually might have to wait. So this is, right, the first queue, and then when the nurse is available, right, the patients go for the service with the nurse. When the service with the nurse is finished, the checkup with the nurse is finished, they might have to wait again before they go to the doctor, right? And then when the service of the doctor is finished, they leave. So actually we're interested in the time from this point to this point, right? How long does it take from the moment patients arrive till the moment they leave? That's what we want to measure. That's our performance measure in this simulation. So first thing, before we even begin the simulation, it's a good idea or the questions may be asked: what is the average time between arrivals, or average inter-arrival, right? Average inter-arrival. This question wasn't asked here, but actually we can ask ourselves, because this is something that we used to compute in queuing systems. We used to, sometimes it was given, sometimes we had to find it out. So what is it? Average inter-arrival time is right, in using our queuing symbols, it's 1 over lambda. 1 over lambda is average inter-arrival time, and it can be computed in this case as the expected value of this random variable, right? If the inter-arrival can be 5, 10, or 15 minutes with those probabilities, the average inter-arrival is just expected value of this random variable. So we can compute it as, right, as what? As 0.5 times 5, 0.5 times 5 plus 0.3 times 10 plus 0.2 times, 0.2 times 15. So if you do the computation here, you get 8.5 minutes. So we know on average patients arrive 1 per 8.5 minutes, and actually we can compute the arrival rate, right? Arrival rate, which is lambda, that is 1 over 8.5 minutes. Now be careful with the unit here. It is if you do the computation, 0.1176 customers per minute, or if you like, it is about 7.059 customers per hour. Right, this is customers per hour. So we know we should expect about 7 customers an hour. That's the arrival rate on average, right? And the same thing we can try to see what's happening here at the doctor's service time, right? As far as the nurse, we know how long the service takes for the nurse. For the nurse, mu, or actually 1 over mu, average service time for the nurse is 7 minutes, right? So we can also compute the service rate of the nurse is 1 over 7 customers per minute, right? Customers per minute, which will be a number of customers per hour. That will be 60 per 7 customers per hour, right? Which is 8.57 customers per hour, right? For the doctor, however, right, I'm running out of space here. For the doctor, 1 over mu is again, right, it's at the average service time, it will be the expected value of this random variable. This is the same thing as here for the average inter-arrival time. Average service time is just 0.3 times 4 plus 0.5 times 8 plus 0.2 times 12. So that, if you do the calculation, which I did before doing this, preparing this this video, is 7.6 minutes. So on average service of the doctor is a little bit longer, and if you compute mu, which is 1 over 7.6 minutes, right, that will give you 0, or I'll put it immediately per hour, right, 7.895 customers per hour, right? That's doctor's service. So we're having here a information about arrival rate, about 7 customers per hour, nurse's service rate about 8.5, 8.6 customers per hour, and doctor's service rate, which is about 7.9 customers per hour, right? And now back to the simulation. If for the simulation, in order to be able to generate random times between arrivals, we have to do the mapping. So we have to first assign or map numbers from a uniform discrete distribution between 0 and 99 to those 3 different times between arrivals. So in order to have 50% chance for time 5 minutes, we need to assign 50 numbers out of 100, which means I have to take the first 50, and that will be from 0 to 49, right? 0 to 49, that's 50 numbers. These are mapped to 5-minute inter-arrival time. Now I need 30% probability. I will take 50, and the next 30 numbers from 50 till 79, right? 79, and then the remaining 20 numbers, which will be 80 till 99, right, will be mapped to 15 minutes. Of course, we should end up using all numbers if this is a complete distribution, right? So now I know if I get a random number from this discrete uniform distribution between 0 and 99, I can then map it to inter-arrival time 5, 10, or 15 minutes in my simulation. We do the same thing for doctor's service time. So if I have 30% chance for 4-minute service time, I have to take 30 numbers, which will be, first 30 will be 0 to 29. Then I will take the next 50 numbers, 30 till 30 plus 50 minus 1, so that's 80 minus 1, 79, right? And the last 20 numbers, again 80 till 99. That's mapped to 12. So I have my random number mapping. Now I can go to the simulation, and here I also prepared a table to just make it a little bit easier on myself. So I have here I will simulate what happens for each customer. I'll have 5 customers just to keep the simulation short. Customer 1, 2, 3, 4, and 5. And I will simulate when this customer arrives. I will simulate what happens when the service starts, finishes with the nurse, and then what the service starts and finishes with the doctor. And then I'll try to compute the time in system, which, as I said, is the measure, the performance measure I'm interested in. We will average it at the end. So in order to generate random arrivals, I have to get inter-arrival times, right? These 5, 10, or 15 minutes, but with proper probabilities, 50%, 30%, and 20%. So I need to use random numbers. Now I've prepared some random numbers using Excel. I used Excel to generate random uniform numbers, and I have the following numbers: 60, 30, 42, 9, and 65, right? So I obtain these random numbers. Now, from Excel, these are uniform integer between 0 and 99. Now I can use my mapping to map those to time between arrivals, or inter-arrival time. This stands for inter-arrival time. So inter-arrival time for the first customer 60 falls into second range, so inter-arrival time is 10 minutes. So I'm going to put here 10. Right? So when does this patient arrive? Well, if we assume that the office opens at time 0, 10 minutes later the patient arrives, so arrival time is minute 10. Now what about the second customer? Second customer, for this customer or patient, a random number is 30. 30 maps to 5 minutes, so there is inter-arrival time 5, and that means this patient arrives 5 minutes after the previous one, which arrived at minute 10, so this one will be at minute 15, right? So basically this column will be cumulative of this column. So the next one, 42, is again 5 minutes, so minute 20. The next one is 9, which is also 5 minutes, that is minute 25. And then the next one, 65 falls again in 10 minute range, so it's 35, right? So we know now when those patients arrive. Now what happens at the nurse's station or nurse's office? So if the first patient, when the patient arrives at minute 10, the nurse should be available, right? We're not going to simulate any delays. The nurse should be there at her station, so the service of the nurse will start at minute 10. And now ST stands for service time. We know it's always 7, right? So it starts at minute 10, takes 7 minutes, it will finish minute 17. That's a simple sum. More interesting is what happens here, right? The patient arrives at minute 15. However, the nurse is still busy until minute 17, right? When the patient arrives, the nurse is busy with the previous patient. So when will the service start? It will start at minute 17. So if you like, this is the maximum of this 15 and 17. We put it here as the start time of this second patient. And of course, it will take again 7 minutes. We said it is deterministic, so it will finish at minute 24. So what we can compute now in this column, which is also for nurse, is the waiting time, right? The waiting time that occurs here before the nurse. The first patient did not wait, so we can put 0 or just dash. And the second patient waited, right? The service started at minute 17, but the patient was ready at minute 15, arrived at minute 15. So there is 2 minutes. The difference between this and this is 2 minutes of waiting time, right? What happens to the next patient? Arrives at minute 20, but the nurse is busy until 24, so we will see that again service will start at minute 24. There will be 4 minutes of waiting. It will take 7 minutes. 24 plus 7 is 31, and so the service finishes at minute 31. And then we go to the next patient. The next patient again has to wait because he's ready. He arrives or she arrives at minute 25, but the nurse is busy until minute 31, so the service will start 31 and take 7 minutes until minute 38, and that is 6 minutes of waiting. And then the last patient again has to wait 38 because he's ready at minute 35, 7 minutes till 45. And of course here there is a little bit less waiting than before, 3 minutes, because this patient arrived 10 minutes later. Okay, so we simulated what happens to those 5 patients until the end of the service at the nurse's station. Or we still have to see what happens at the doctor's. So again, as with the previously with the nurse, with the doctor, the first patient comes, we will assume the doctor is already there in the office waiting for the patient. The patient finishes at the nurse's station at minute 17, so he can start immediately at minute 17 at the doctor. And again, to generate service time for the doctor, we need a random number. Now, we shouldn't use the same random numbers as for the arrivals, because we would have a correlation between arrival times or inter-arrival times and service times. And we don't want to have this. Therefore, we should use some new random numbers. Again, I prepared some random numbers here, and I have 18, 74, 13, 30 and 53. Right? Such random numbers, if you have an exam question, you should be provided with these numbers, because you cannot make them up. They wouldn't be really properly uniformly distributed. So random number 18, now we look at the mapping. It falls into the first range, so service time is 4 minutes. So if the service started at minute 17 and takes 4 minutes, it will finish at minute 21. Right? Was there any waiting? No, this is the first patient, no waiting happened. Second thing, what happens for the second patient? The patient finishes at the nurse's station at minute 24, the doctor finishes at minute 21, right? So let me just show you this. So these two, right? In this case, the doctor has to wait, right, for the patient, because he finished before even the patient is ready. So here, this is again maximum of those two, but now it's the doctor that waits, not the patient. So the patient again doesn't wait. Service time, we take the random number 74, we see it falls into the second range here. So it's 8 minutes of service time. So if the service started at minute 24, finishes plus 8, finishes at minute 32. And let's look at the third patient. The patient finishes at the nurse at minute 31, but the doctor is busy until minute 32. So the service will start at minute 32, which means 1 minute of waiting, right? And then again 13, we map it back through this mapping to 4 minutes of service. So that means the 32 plus 4 finish time is 36. And the next patient, minute 38, finishes with the nurse. The doctor is ready already because he finished with the previous patient at minute 36, so the start will be 38, no waiting. Service time from 30, it falls in this range, so it's 8 minutes. And 38 plus 8 is 46. So the end of the service is 46. And again, if you look at the next patient, he's ready at minute 45, and the doctor is busy until minute 46. So there will be 1 minute of waiting start here. 53, we map it through this, again 8 minutes of service. So 46 plus 8, 54, right? So we have 54. The service finishes at minute 54. So now the time in system, we have to look at, right, which columns. We have to see when the patient arrived and see when the service at the doctor finished, because that's the whole time, right, from the beginning till the end of the time in the system for each patient. So we see 21 minus 10. So this patient spent 11 minutes in the system, right? The next patient, 32 minus arrival time was 15, right? So this time is 17, right? And so on. We can compute the remaining times: 16, 21, and 19. So you see those patients, their time in the system varies. And now the interesting thing is to look at is the average, right? Average of this is what we're interested in this simulation. What's the average time patients spend in the system? Well, we would have to add all those. So we take the sum of the above, right? And divide it by 5, because we just simulated 5 customers. So if you do the computation here, you'll see average time the patient spends in this simulation, 16.8 minutes. And of course this is just one experiment, and actually a very short experiment. If we would like to get a better estimate, we should first of all simulate more than 5 patients. It would probably be a good idea to simulate something like the whole day, and then not just run one experiment. This is just one experiment. We should probably run multiple experiments like this, and then do statistical analysis to find out, for example, 95% confidence interval for this average time a patient spends in the system. Another question that is also interesting is, right, what is the average number of customers in the system? right? If you think about this, that is our L from the queuing systems, right? What's the average number of customers that are there in this system? Now, if you remember, we can compute this using Little's law. L equals lambda times W. And lambda, if you recall, we have it here. That's our arrival rate, right? And what about W? What is the time a patient spends in the system? Well, that's this value, right? Here we have it. W is here. We just computed it from this simulation. Our best estimate is 16.8 minutes average time in system. So actually we have all the data to compute average number of customers in the system. Just be careful with the units. If this is in minutes, you have to take here the value of lambda, which is number per minute, or if you take per hour, you have to do the conversion. So it is actually 0.1176 times 16.8, and if you do the computation here, you will see we have 1.98 customers. On average, we have around 2 customers present in the system, right? So that concludes this first simulation, manual simulation of a queuing system.